Last class we talked about how we can analyze experimental concentration profiles for getting interdiffusion fluxes within the diffusion zone. Today I would like to talk about various methodologies that we can use for determination of interdiffusion coefficients in multi-component systems. We will first start with determination of fluxes, and hence the analysis of interdiffusion fluxes becomes very important. So, we have seen for binary it is very simple, because there is only one interdiffusion coefficient that describes the interdiffusion flux of both the components. And so, we can get d tilde as minus j tilde over dou c by dou x. So, at every composition plane within the binary diffusion zone, we can determine the value of interdiffusion flux of any component, let us say 1 here, and the gradient of that component at the same plane, and we can divide to get the interdiffusion coefficient at that particular composition. And we can do this throughout the diffusion zone, and we can get the binary interdiffusion coefficients as functions of composition. As we increase the number of components, the complicacies increase. So, if we consider ternary diffusion couple to start with, in ternary we know there are two independent fluxes. So, if we consider the system, let us say 1, 2, 3, and if we treat 3 as dependent component, we can write J1 tilde equal to minus D11 tilde 3 dou C1 by dou x minus D12 tilde 3 dou C2 by dou x, and the second independent flux J2 tilde is equal to minus D21 tilde 3 dou C1 by dou x minus D22 tilde 3 dou C2 by dou x. We have 4 interdiffusion coefficients. So, at any composition plane of a single diffusion couple, we can get only 2 equations, one for J1 tilde, the other for J2 tilde. And so, we cannot evaluate the entire set of interdiffusion coefficients with a single diffusion couple. So, obviously, I need more than one diffusion couple, and since these interdiffusion coefficients are functions of composition, we want to make sure that there will be a common composition in the diffusion zones of the independent diffusion couples that we assemble. So, Kirkcaldy had proposed originally this approach. So, let us call it Kirkcaldy's approach. So, as per Kirkcaldy's approach, for a ternary system, we need two independent diffusion couples with intersecting diffusion paths. So, what is a diffusion path? This is an important concept that I would like to explain now before I go further in Kirkcaldy's method. So, a diffusion path, simply speaking, is the sequence of compositions that develop within the diffusion zone of a couple plotted onto the isotherm. So, if we consider a ternary isotherm, it can be represented by an equilateral triangle which is referred to as Gibbs triangle. So, the three corners of the triangle represents 100% of the three elements 1, 2, 3. Each side of the triangle represents the binary system. So, this is 1, 2 binary, this is 1, 3 binary, and this is 2, 3 binary, and any composition that lies inside the triangle is a ternary composition. I would explain in little more detail the ternary isotherms as we would need it for multiphase diffusion. I will explain it in a separate class, but right now it is just sufficient to know this. Now, if we consider any, let us say, ternary diffusion couple, let us say %% of 1, 20% of 2 and 30% of 3, which is, wait, let's say 20% of 1, 50% of 2, 70% of 2 and 10% of 3. So, if we draw the initial concentration profiles, this is my C1 minus, 50 and 20, this is C1 plus, this is C2 minus 70, this is C2 plus and 30, C3 minus, C3 plus. So, after diffusion annealing for certain time, it will develop the concentration profiles. This is for 1, this is for 2, this is for 3. As the diffusion time increases, we know the diffusion profiles will broaden. So, the composition profiles will change with time. That means, each composition plane will move with time, and we know how each composition plane moves parabolically. That is, C is a function of x over root t, this we have seen, and x over root t is the Boltzmann parameter lambda. If we plot this sequence on the ternary isotherm, so let us say if this is my alloy 1 and this is alloy 2, somewhere is here is my alloy 1, alloy 2, here is alloy 2. So, I first mark the terminal alloy compositions alloy 1 and alloy 2 on the ternary phase diagram. I am showing the straight line joining the two compositions by this dotted line. Now, if I plot the composition sequence that is developed in the diffusion profile onto this ternary isotherm, what would be it like? One may tend to think that it will follow this straight line joining the two terminal alloys, but it is not the case. We will find typically this sequence of composition, if plotted on a ternary isotherm, takes shape of S. So, the diffusion path is typically an S shaped curve. And what is the significance of diffusion path? The significance of diffusion path is that it is independent of time, or it is invariant with time. We have seen, if we plot concentration versus distance, x axis here is this distance coordinate, it is a function of time. With time, each composition plane is moving and the diffusion profile is broadening, but not so with the diffusion path. And this is because in an infinite diffusion couple, the composition, each composition plane moves parabolically with time. It is a function of Boltzmann parameter lambda. There is no new composition plane added or any composition plane getting removed, and so obviously the sequence of composition will not change, although the profiles will broaden with time, and so the diffusion path is independent of time, and this is an important concept. When we conduct the diffusion couple experiments, in order to assess the reliability of our experiment, we should usually prepare at least one diffusion couple 3-4 different times, the same couple, that is the couple between the same two terminal alloys annealed for 3-4 different times. I have to make sure that at different times the diffusion paths are same. So, that helps to establish the reliability of the experiments. Now, coming back to Kirkcaldy's method here for determining ternary interdiffusion coefficients, we want two independent couples. So, if we consider, draw this ternary isotherm again, let us say I prepare two independent couples, one between alloy A and alloy B, and the other between alloy C and alloy D, and these two couples should be such that their diffusion paths should intersect. So, if I prepare the two diffusion couples such that the straight line joining the two terminal alloys, they intersect, there is a high possibility that the diffusion paths of the two will intersect. So, this may develop S-shaped diffusion path, both of them will develop S-shaped diffusion path, and they will intersect at some composition. Let us denote this by P. The two diffusion paths are intersecting at point P, which means the composition P is common to both the diffusion couples AB and CD. And why it is important? Because at point P, or at the composition corresponding to point P, in each of the couple we can write the two independent flux equations, right, one set of two equations for couple AB, the second set of independent equations for couple CD, and this way we have 4 independent equations, and now we can solve those for the 4 interdiffusion coefficients, and those 4 interdiffusion coefficients will correspond to the composition at point P, and these are the exact values of the interdiffusion coefficients, the ternary interdiffusion coefficients. In order to get interdiffusion coefficients at different compositions, we need to prepare such intersecting path diffusion couples and get the values. Now, it is not possible to predict the diffusion path exactly. So, we cannot design really the couples, we cannot really design the diffusion couples whose diffusion paths will intersect at the exact desired point, but we can kind of design the couples this way, so that the line joining the two terminal alloys intersect. So, we know somewhere they will intersect, okay. And this way this method has been applied to many ternary systems, and the interdiffusion coefficients have been determined. So, this analysis was for the ternary systems. In principle, Kirkcaldy's method can be extended to an n component system. For example, in quaternary we have 3 independent fluxes J1, J2, J3, which are expressed as functions of 3 independent gradients. So, there are 9 interdiffusion coefficients at any given quaternary composition. So, if we extend this analysis to quaternary, we will need 3 independent diffusion couples which will intersect at, we will need 3 independent diffusion couples whose diffusion paths will intersect at one point. Now, it is highly difficult to design such couples. Quaternary system, for example, an isotherm is a 3D figure, like in ternary it is a 2D figure because there are 2 independent concentrations. In quaternary there are 3 independent concentrations and it will be a 3D figure. Now, imagine 3 curves, that is 3 diffusion paths in 3 dimensions intersecting at one common point. It is almost not practical to design such couples. However, recently there has been one approach proposed that I will discuss next, but so far it was not possible, and so in principle this method can be extended to n component system, but practically it had not been possible so far. But recently John Morrell has proposed an approach called body diagonal diffusion couples, which we can use in limited cases in order to get quaternary, quinary or even higher component interdiffusion coefficient matrices. I will explain that approach now. So, body diagonal diffusion couple approach is essentially extension of Kirkcaldy's approach to n component system, but it just gives a systematic way to design the multi component diffusion couples such that they would intersect possibly at one point. So, I will explain this with the help of a quaternary system, and then I will explain how we can extend it to the higher order systems. So, when I consider a quaternary system, I need 3 independent concentration variables to define one quaternary composition. So, if I plot a particular composition, I need a 3D composition space. The fourth one is of course dependent. So, if I design a couple between, let us say, alloy 1 and alloy 2, I have 2 terminal alloys with concentration, let us say C11, C21 and C31 and C12, C22 and C32. The difference between the corresponding concentrations of the 2 terminal alloys is denoted as delta Ci, and the composition vector delta C0 is written as delta C1, delta C2 and delta C3. In body diagonal diffusion couple approach, the terminal alloys are selected. So, this is the composition vector delta C0. Now, consider a composition C bar and imagine a cube around this composition C bar, such that C bar is at the body center of this cube, and this cube is drawn in a 3D composition space of C1, C2 and C3. So, the C1 axis is this one, C2 is coming out of the board and C3 is this one. In body diagonal diffusion couple approach, the two terminal alloys of a diffusion couple are selected from two ends of a body diagonal of this cube, and that is why the name body diagonal diffusion couples. Now, why it is significant, that you will realize soon. So, we have, for example, in quaternary there is a cube here. For a cube there are 4 body diagonals, and we can so form 4 such sets of diffusion couples. Now, what is the special feature about the body diagonal couples? They are characterized by same difference in concentrations for 3 independent components. So, if we determine the difference between the concentrations of any two alloys selected from the two ends of the body diagonal, the 3 components will have the same difference of the concentrations. The 4th one of course may be different, because it will make up for the total to be 100%. Now, if I imagine the origin 0 0 0 to be at this C bar, that is at the body center, then I can mark the 8 corners of the cube in terms of delta C0, or more specifically in terms of delta C0 by 2, because delta C0 is the composition vector, and I have to select the terminal alloys from the ends of the body diagonals. That is, the terminal alloys are from the 8 corners of the cube. So, obviously, this corner will be delta C0 by 2 1 1 1. This will be delta C0 by 2 be 1 bar 1 1. This will be delta C0 by 2 be bar 1 1. This will be delta C0 by 2 bar 1 1. Then this will be delta C0 by 2 bar 1 bar 1. This will be delta C0 by 2 1 bar 1. This will be delta C0 by 2 1 bar 1 bar 1, and this here would be delta C0 by 2 bar 1 bar 1 bar 1. So, since there are 4 body diagonals, we can have 4 sets of diffusion couples, and if we select a specific C bar and specific delta C0, we can write down the compositions of all the alloys on the 8 corners of the cubes. Right. So, if we write those compositions, now the question is why it is important to select the terminal alloy concentration from the 2 ends of a body diagonal, because if delta C is very small, then we expect the interdiffusivity matrix to be more or less constant throughout the diffusion zone, and if the interdiffusion coefficients are constant, then the diffusion path is symmetric, which means for any of these body diagonal couples, the diffusion path will intersect the body diagonal exactly at the body center position, that is exactly at C bar. So, we can have in quaternary, for example, 4 diffusion couples whose diffusion paths are expected to intersect at one single composition C bar here, and this way the body diagonal diffusion couples help us to design the diffusion couples which will intersect at one desired composition. So, the steps are easy. We select C bar, which is the desired composition at which interdiffusion coefficients are to be evaluated. Then select particular delta C, the small composition difference in which we expect the interdiffusivities to be constant. Then we form a cube around C bar with the composition vector delta C based on these coordinates, and prepare the body diagonal diffusion couples. Now, for quaternary we need 3, and since there are 4 body diagonals, we can form actually 4 diffusion couples. So, there will be more than sufficient number of couples. To get the variation with composition, we can shift C bar and form new sets of couples. Okay. So, let us see an example here. So, let us say I want the quaternary interdiffusion coefficients at C bar equal to 25, 25, 25% of 1, 2 and 3. So, obviously, the component 4 will also be 25%, and delta C0 is 10. With this, the center here is 25, 25, 25. I need to find out the 8 corner compositions, and these coordinates will help me to do that. Okay. So, 1 1 delta C0 by 2 1 1 1 means I need to add 5 5 5 10 by 2 5 5 5 to this to get the composition of this corner. So, this corner will be, so if I form the first couple as A B here, this is my body diagonal, the composition of A is 25 plus 5 plus 5 plus 5. So, 30 30 30. So, obviously, component 4 is 10, composition of B is minus 5 minus 5 minus 5. So, it will be 20 20 20, component 4 will be 40. So, we can see the difference is 10 10 10 for all 3 independent components. The fourth one is different because it has to make up for the total weight percent to be, or the total atom percent to be 100%. The second couple can be, let us call this C D. So, the composition of C is -5 -5 5. So, that will be 20 20 30. So, 30 plus 20 50 70. So, the remaining will be 30. Composition of D would be +5 +5 -5, 30 30 20. Remaining will be 20. Then E F, the composition of E would be -5 5 -5. So, 20 30 20. Remaining will be 30. Composition of F would be 30 20 30, 30 20 30, remaining would be 20. This is F. Let us denote the fourth body diagonal, this as G, this as H. So, G is -5 5 5. So, 20 30 30. 20 30 30. So, the remaining is 20, and H is 5 -5 -5. So, 30 20 20, 30 20 20. This will be 30. And this way we can design 4 sets of diffusion couples with 8 terminal alloys from 8 corners of the cube, which is formed around C bar with and the couples would be with the composition vector delta C 0. We can see for each of the couple, components 1 2 3 have the same difference 10 10 10. The fourth one makes up for 100%. Now, since the 4 diffusion couples are expected to intersect at one composition C bar, we can form 9. Since we can get 4 diffusion couples whose diffusion paths are expected to intersect at the body center position C bar, we can select any 3 of them for our experiment, so that at the common composition C bar we can get 9 independent equations, because there will be 3 independent fluxes in each couple at the common composition. So, we can write 9 independent equations and we can solve for 9 quaternary interdiffusion coefficients. This method we can extend even to quinary and higher order system. In principle, in higher order systems, we need to imagine the hypercube formed in n-1 dimensional space. In n-1 dimensional composition space. Like in quaternary, there was a 3 dimensional composition space, and we can get 4 body diagonal diffusion couples. In quinary, in an n component system, we have n-1 dimensional composition space, and there would be 2 to power n-2 body diagonals possible. So, for example, in quinary, if we imagine a 4 dimensional hypercube, there will be 2 to power 3, 8 body diagonals. In quaternary, we have already seen in 3-dimensional composition space there will be 2 to power 2, 4 body diagonals, which I already got. Ternary, it is simple, it will be a square and there will be 2 body diagonals, 2 to power 1, 2 body diagonals. And this way we can extend this method for higher order system. We have applied this to quaternary as well as quinary system, and I will illustrate the application part of it for all, each of the system, binary, ternary, quaternary, quinary of the methods. So, we have seen how we can get the interdiffusion coefficients in binary, ternary, quaternary and higher order systems. I will also give some examples from the literature of actual determination of interdiffusion coefficient sets in practical systems. That will be in the next class. Now, these are the methods which give exact values of entire sets of interdiffusion coefficients. Now, there are also some additional techniques, because it may not be always possible to design such couples. For example, in the body diagonal coupled approach, one limitation is we need a large enough single phase region, because if there is no large enough single phase region, we will not get enough space for this cube, for example in quaternary, to form. Also, there is a possibility that one of the diffusion path may cross the single phase region and it will be a multi phase diffusion couple, again which is not desired. Right. So, it is not always possible to form such couples. So, in that case we can have access to at least some of the diffusion coefficients, and there are a few techniques that we can use for that. So, I will talk about those techniques now. So, we have seen in multi-component systems, it is frequently observed that some components develop maximum or minimum on their concentration profiles. So, one such profile I have shown here. So, let us say this is an infinite diffusion couple C I minus, let us say this is component 2. So, C2 minus is the left terminal alloy concentration, C2 plus is the right terminal alloy concentration, and this peak is of interest. Why? Because we can get at least couple of interdiffusion coefficients in ternary system out of 4. So, if this happens in a ternary system, for example, if I treat 3 as dependent component, I can write 2 independent fluxes as J1 tilde is equal to minus D11 tilde 3 dou C1 by dou x minus D12 tilde 3 dou C2 by dou x, J2 tilde equal to minus D21 tilde 3 dou C1 by dou x minus D22 tilde 3 dou C2 by dou x. At the maximum, the gradient of component 2 is 0, which means dou C2 by dou x is 0. So, I can get rid of the second term in both the flux equations. So, essentially I can get 2 values D11 and D21 with respect to 3 as component, 3 as dependent. Right. So, this gives me at the composition corresponding to I can get D11 tilde 3 as minus J1 tilde divided by dou C1 by dou x and d Q1 tilde 3 as minus J2 tilde divided by dou C2 dou C1 by dou x. Okay. So, this is how we can get interdiffusion coefficient at a maximum or minimum, of course not the entire set, but at least some of them. So, this gives us an idea about main interdiffusion coefficient of 1 and also the kind of interaction that one has with 2, that is how the gradient of 1 can affect the diffusion flux of 2. Also we have talked about ZFPs or zero flux plane yesterday. These are also important to the point of view of understanding the interdiffusion coefficients here. So, let us say we know how to determine the zero flux plane. So, if there is a minimum or maximum form, we expect that there may be a zero flux plane. It is not necessary that there will be, but there may be, and we know how to find it. So, we find an area under this peak here and we find an area on the right hand side such that this area equal to this area, and we know that the zero flux plane will be here. So, this is the ZFP for 2. Now, why this is important? Because at ZFP J2 is 0, which means these two terms are equal, and so we can get the ratio of D22 tilde 3 to D21 tilde 3, which should be equal to minus dou C1 by dou x divided by dou C2 by dou x, and these gradients are evaluated at the location of ZFP. Remember, the gradient is 0 at the peak, not at the ZFP. Okay. So, at ZFP both 2 and 1 would have developed some gradient, and so we can get the ratio of main coefficient to cross coefficient. This gives a good idea about how significant the interactions are, because if the interactive coefficient is about similar order of magnitude to the main coefficient, then the ratio would be close to unity. If the interactions are more dominant, the ratio would be less than unity. If the interactions are less dominant, the ratio would be more than unity. And the sign of course gives us an idea about what kind of interactions these are, because assuming D22 is positive, the sign will tell us whether D21 is negative or positive. Okay. So, this is how the zero flux planes and maximum and minimum will give us an idea about at least some of the diffusion coefficients or the diffusional interactions. Then there is another approach proposed which is called pseudo binary. This pseudo binary approach is proposed by Alok Paul . So, and this is applicable to get main coefficient of at least one component in a multi component system. In this, what is done is, so for example, if we are dealing with a quaternary system, only 2 of the components will develop concentration profiles in the diffusion zone, the remaining 2 will not. So, the diffusion couples are designed such that, for example, to start with component 3 and 4, let us say, have the same concentration in both the terminal alloys, but component 1 and 2 will have different concentrations. So, how it helps? So, let us say if I write the equation for the independent fluxes, let us say J1 tilde is minus D11 tilde 3. In quaternary, let us treat component 4 as dependent. So, in quaternary system we have 3 independent fluxes. If we treat component 4 as dependent, we can write J1 tilde equal to minus D11 tilde 4 dou C1 by dou x minus D12 tilde 4 dou C2 by dou x minus D13 tilde 4 dou C3 by dou x. And suppose we have selected the diffusion couples such that only component 1 and 4 have different concentrations in the 2 terminal alloys, but component 2 and 3 have same concentrations. Assuming that they will not develop any concentration profiles during diffusion, these two terms will be 0 and we can straight away get J1 tilde 4 divided by dou C1 by dou x, there is a negative sign here, equal to D11 tilde 4. So, we can find the value of D11 tilde 4 through the pseudo binary diffusion couples. So, of course, it will not give the entire set, but it gives an idea about at least how the how fast or slow a particular component is diffusing based upon its main interdiffusion coefficients. We can design such couples to get different main coefficients, and we can find out the main coefficients at different compositions based upon the pseudo binary technique. The advantage is this can be applied to any component system as long as only 2 components develop the composition profiles. But the limitation is we are assuming that the interactions are not significant, because if the interactions are significant, even if we start with the same concentrations of, for example, 2 in both the terminal alloys, it will end up developing some concentration profile, because there will be an uphill diffusion region developed, which is not desired for the pseudo binary couple, because in that case then we cannot solve for D11 tilde 4 directly. Similarly, a pseudo-ternary approach has also been proposed, in which instead of 2 here we will have 3 varying concentrations and remaining constant. And if we can design 2 such couples with the same set of components which being invariant and having at least one common composition in the diffusion zones of the 2 couples, similar to the Kirkcaldy's approach at for ternary that I explained, we can solve the 4 equations at the common composition and get 4 independent interdiffusion coefficients. Again, it will not be an entire set, because in quaternary, for example, we need 9 interdiffusion coefficients, and so through pseudo ternary couples, if we can form such couples, we will get 4 out of the 9 coefficients. Again, one assumption there will be all the components which are supposed to be invariant will not develop any uphill diffusion region, which means they will not exhibit significant diffusional interactions from the other components. Okay. So, these are some of the experimental techniques which we can use for determination of interdiffusion coefficients in multi-component systems. In the next class, I will show you some specific examples from the literature in which such estimation of interdiffusion coefficients has been reported. We will stop here for now. Thank you.